Okay? Okay, everyone. So far we looked at solving forces into components in 2D using angles and ratios. And just a reminder, the reason that we're doing this ahead is this is really not part of statics. This is stuff that you should know before we get to statics. And I just want to make sure that we're spending a lot of time on statics. So I want you to come in prepared. And a lot of what I covered in the first video and this video is really learning how to communicate as an engineer rather than a physicist or a mathematician. Because you came from math and physics, and now you have the foundation on which you're moving into engineering, and you're all engineering majors. So just to go over some of the rules, we learned that unit vectors, we always represent them to 4 decimal places. Direction angles, and direction angles are the theta x, the theta y, and theta z. And just as a reminder, theta x is the angle between the force in question and the positive x-axis. Theta y is the angle between the angle in question, the force in question and the positive y-axis. And theta z is the angle between the force in question and the positive z-axis. And remember that each one of these values can have 2 values. We saw that. We also learned that when we represent components, we want to represent it in 1 decimal place. These are force components, 1 decimal place more than the given force. We also learned that representing vectors, there are 3 different ways to represent vectors. One is in vector form, which you probably referred to it as Cartesian vector form before. Fxi plus fyj plus fzz. And actually, also I know you've also seen it written this way. Fx, comma, fy, comma, fz. So you have the triangular brackets on the sides, and then you put fx, fy, and fz with commas between, and you do not write I, j, or k. Either one is fine. And then magnitude and unit vector, and magnitude and direction angle. So those are the 3 ways to represent vectors. And then we did 3 different checks. We did a magnitude check, a unit vector check, and a visual plus or minus check. So these are the rules that we already covered, and now we're moving on to 3D problems, and we're going to make sure that we apply all these rules as we go through it. So let's move over to this problem now. So this is a 3D problem, and since distances are given, is this an angle problem or a ratio problem? It's a ratio problem. Because we don't know the angles, and we'll probably find the angles at the end, but we're not going to use angles to find the components. Instead, we're going to use the ratios. So let's first take a look at this picture. It's very, very important in 3D problems that you first look at the axes. In this case, x and y axis is on the horizontal plane, and the z-axis is the vertical plane. That represents, it's usually drawn like this because xy represents our plane. If you think about the Earth, we're looking at an xy plane or north, south, east, west plane, a horizontal plane. And then the vertical plane really represents the elevation. So there are times you're going to see the axis with x and y on the horizontal and z going up. And I'm hoping that in the video you can see this. Here are my PVC pipe axes. So the x-axis is coming out at you, the y-axis is here, and the z-axis is going up. Okay? So this is one way. So our red color represents our force, and in this case, the value of the force, let me look it up. And while I'm looking it up, take a look at 1, 2, and 3, and what distances do those represent? So the value of the force is 21 kilonewtons. So of the 1, 2, and 3, which is the distance in the x direction? So take a look at your x-axis, and which distance is parallel to the x? The 1. I'm going from the bottom front right corner of the box to the top left back corner of the box. So am I going in the positive x direction or the negative x direction? 1 unit. I'm going a -1. Okay, how about in the y direction? What value here, which distance here is parallel, is along the y-axis, and it's a 2. When the force goes from this origin point up to here, is it going in the positive 2 direction or the negative 2 direction? Negative 2. And then looking for the z-axis, the force going from this point to this point, it's going up, so it's going in a positive 3 direction. The biggest problem that students have in this part of statics is being able to visualize things in 3D. Now, I'm hoping all of you have taken Engineering 25, maybe some of you are taking it right now. A big skill that you get in that class is being able to see things in 3D. If you have a hard time seeing it in 3D, you're going to have to do more practice now on 3D problems, because you have to be able to visualize it. Okay, so we have a distance of 2, negative in the x, 1 negative in the x, 2 negative in the y, and 3 positive in the z. But we also need to know the total distance. Remember when we did a 2D problem, and we had a force going off here, and we knew it was a 4, 3, 5 triangle? We weren't given the 5, but we knew the distance in the x was 4, and the distance in the y is 3, and from Pythagorean's theorem, we knew this was a 3, 4, 5 triangle. Well, we can use Pythagorean's theorem in 3D too. As I'm sure you figured out now, the distance, the total distance here, is going to be equal to radical of x squared plus y squared plus c squared. And we can put the negatives in if we want or not, because we're squaring them. So x was 2, 2, 3. What's that come out to? 9 plus 4 is 13. Did I say that? 9 plus 4 is 13, 14, radical 14. And we want to keep it in this form. We want to keep it as a radical. Because if we change it to a regular number, we're going to have some rounding errors. So just as in the 2D problem, when we were very methodical, step by step, we're going to be very methodical here. So our force, remember, our force is equal to 21 kilonewtons, and the units go on the right side, the magnitude goes on the left. And what does this part represent right here? What does this part represent? The 21 is the magnitude of that force. This is the magnitude. What does this part represent? Our unit vector, our direction. Because we're dealing with vectors. Direction, sorry. If we're dealing with vectors, we have to have a magnitude and a direction. So we said that in the x, it was going -1, and it's 14I. In 2, we said -2, radical 14j, plus 3 over radical 14k. And this turns out to be 21 times -0.2673 I minus 0.5345j plus 0.8018 k kilonewtons. And a solution of our answer comes out to be -5.6 I minus 11.2j plus 16.8 k, and the units are kilonewtons, and here's my value. So let's look at a few things. 1, how did I represent this? This is represented in vector form. So here I represented the vector in vector form. This we said is our unit vector. So if we have 3 ways that we can represent our forces, we have vector form, we have magnitude and unit vector, and magnitude and direction angle. But before we represent it in the other 2 ways, I want to make sure that we're doing our checks. So let's do our checks in red. So what is the force check, the magnitude check? Well, Pythagorean's theorem. 5.6 squared plus 11.2 squared plus 16.8 squared under the radical. I do it on my calculator and I get 21. Okay. So I checked the magnitude. What else could I have? I could do a unit vector check. And how do I do that? 0.2673 squared plus 0.5345 squared plus 0.8018 squared, and it comes out to be 1, so that checks out too. And then we need to do our third check, which is the plus or minus visual check. So let's take a look. We got a value of a negative x. Is it going in the negative? Yes. We got a value of a negative j, negative y. Is it going in the negative y? Yes. I got a value of a positive z. Is it going in the positive z direction? Yes. Okay. So I set it up in step by step, first step, second step, third step. I did my 3 checks, and now I'll move on. So I first set out, represented my vector. My vector was represented in vector form. Now I'm going to represent it in magnitude and unit vector. And what did we say unit vector was? It's usually represented as E in static, negative 0.2673I minus 0.5345J plus 0.8018K. Any units on that? No, because it's unitless. The last way to represent the vector, so this is magnitude and unit vector, and now we're doing magnitude and direction angles. So force we know is equal to 21 kilonewtons, and now we have to solve for what theta x is, theta y is, and theta z is. And how can we do it? Remember, from looking at it in 2D, when we did the 2D problems, we could either look at this value, which is the unit vector x component. We could look at it in 4 decimal places, or we could look at the force in the x divided by the total value. So let's do it in 2 different ways. So the theta x is equal to the inverse cosine of 1 over radical 14. We'll do the same thing here. Cosine, inverse cosine of negative 2 over radical 14, and the inverse cosine of 3 over radical 14. And the values that we get are 105.5 for theta x. Theta y we get 122.3, and theta z turns out to be 36.7 degrees. Are we following the right rules? Unit vector is 4 decimal places. Have it listed as 4 decimal places. Direction angles, 1 decimal place. 1, 2, 3. Components, 1 decimal place more than given. We were given as 21 kilonewtons, no decimal place. Our value is represented to 1 decimal place. Let's go back to direction angles. I used the unit vector, but I could have also said theta x is equal to the inverse cosine of fx over f, which is inverse cosine. Fx is negative 5.6 over 21, and the answer would come out to the same, or close. So you could find the direction angles by using the unit vector, or you could find the direction angles by saying the x component for the theta x, the x component over the total magnitude of the force. Okay. Let's take a look at this. What do you notice about theta x and theta y? Let's do it over here. Theta x and theta y are both obtuse. But theta z it again, maybe you can see this. So here's my x-axis, here's my y-axis, and here's my z-axis. Here's my force. You see the arrow on here? This is my force. We know that it is going in the negative x, so it's going back towards me. We know if it's in the negative y, it's going in the negative y direction, and it's going in the positive z direction. So does this make sense? The location that I put this PVC pipe, this force vector, is the same as that. It's going in the negative x, it's going in the negative y, and it's going in the negative z. So now let's think about theta x, theta y, and theta z. The theta angles, the direction angles, represent the angle between the force and the positive axis. Does it make sense that since the force is right here, this is my theta z? It is an acute angle. But because this force is so far from the x-axis and so far from the y-axis, it actually is obtuse there. It's maybe a little bit difficult to see where this is. Let me try to do it with a piece of paper. Let me see if I can hold this, yeah. Let's bend this. Here's a piece of paper. Theta x, let's do theta z first. Theta z is the angle. It's the most direct angle to get this force to the positive z-axis. It's this angle right here. It's acute. The angle from the force to the x-axis is this guy in here. It's this whole angle here, which is an obtuse angle. It's this angle. It's this angle right here. And the angle to the y-axis is this angle. It's the most direct path, the shortest angle to the positive y-axis. So when we have a negative, if we have a force going in a negative direction, and we did in the x and in the y, our theta is going to be obtuse. But when we have a positive value in this case it was z, positive value in the z is going to give me acute angle. Let's see if I can, I think the z angle you kind of figured out. Here, this is theta x. It's this angle right in here, that's theta x. It's the most direct angle that it gets from this force to this angle, to this axis. Well, let's do y.